soldier forward and cover logical agents, because this is an important part of system design and programmatic design in general. If your problem makes sense to represent in terms of a knowledge base, what you know, what you don't know, and the associated logical interactions. So on the very first day of class, I said we're going to be diving into propositional and predicate logic, and it's going to be kind of assumed that we know what we're talking about when we utilize some of that language. That day is today.
You're bad, bad man.
Discrete comes back over and over and over, again and again, again, because it is relevant to a lot of knowledge representation. I don't know what was going on in my brain when I wrote this motivation slide. You can tell I was just not having a good day when I did it. And so here's the entire motivation of this slide deck. It's like, I don't even know if I need to go into more detail than this, but humans can occasionally do intelligent things based off the things that they think they know. So if we can figure out how humans know things, we can get computers to also know things and intelligently reason about their environment to make decisions based on that. But every time I talk about logic, I have to give this one point of contention, because knowledge bases work incredibly well as long as they are pure. And what we know about knowledge bases is as soon as you input a single falsity into that knowledge base, you can propagate that to create an infinite amount of false knowledge using perfect logic. So even though your process is perfect, as soon as you hear someone say something that is not true and you believe them, using perfect logic, you can generate an infinite number of false, what you would consider to be facts, and then start to spread that. So that is how misinformation is born, is as soon as one logical person believes one incorrect idea, the entire population can believe an infinite amount of false information, which is kind of fun when you try to apply it to society at large. There's something to be said there about we as humans don't care quite enough to try to keep our knowledge base pure, or we think that our knowledge bases are pure when they are very much not pure. As soon as we have a disagreement about something that is binary in nature, one of us must be wrong about
I disagree.
it. Well, one of us is wrong about that. So how do we actually represent knowledge in a knowledge base digitally? Because this can be very important for security implementing as well. So you can imagine that the knowledge of the health of your system, what's going on, is related to how every internal system is functioning or not functioning, the data that you actually gather. So you could store the health of your system in terms of a knowledge base. Let's consider what a knowledge base agent might actually look like. So all they are sentences, facts, truths, however you want to call this, but they're the facts of the world that the knowledge base agent cares about. So whatever its domain is, what's in that knowledge base are relevant truths about that world. And there are a couple ways to set this up. The next slide, we'll get into that a little bit. But we define this concept of an axiom as just a sentence that is given by the programmatic overlord. It's not something that you derived from what you know, it's something that you were told. So it becomes the basis of information. So yeah, two kinds of knowledge: the knowledge that we are told and believe, and the knowledge that we derive from that. So to set up a knowledge base, the initial state of that knowledge base will just be all of the axioms that you, the programmatic overlord, feed it. And it is your task to make sure that everything that you set up is true. Because again, as soon as you have one false axiom, you can derive a bunch of falsehoods. So keeping those axioms pure is incredibly important. What can you do to a knowledge base? Two really important things. You can tell a knowledge base something. This is a way of feeding it information. Here is a fact. Incorporate it into your knowledge base. You can ask and say, via logic, can you deduce an answer to this query? And usually that query has to come in the form of a yes, no, but sometimes you can, if you use predicate logic especially, be able to get back objects from that. So this can be something like, who is the father of John? And using the associated knowledge base and representations of these, this is using predicate logic now, but using those functions, you can find the answer to that query by doing something intelligent to derive that information from what is in the knowledge base. So yes, both the tell and the ask can involve inference. At that point, using the tell to derive new statements of fact from everything else, because what you tell it might be related to other information that it has in some capacity. Using logical inference, it can now derive new facts about the world. When you ask it, as it derives new information, it can start adding that back into the knowledge base because it's derived some information that might not be incredibly useful at the moment, might not directly answer the query, but maybe it helps to answer a later query. And as you spend the time, the system is spending the time to understand the world around it and to derive new facts, you just add those back into the knowledge base, and those can be shorthands for later. So of course, everything has to be derived logically. You're not going to make up anything. You're not going to guess anything. You want to keep your knowledge base pure. So here is a very simple knowledge base agent. Takes in an associated set of percepts. What is the state of the world around me? Returns an action to do within that realm. So this is a way an agent acts in a state and decides based on what it can do, the action to take based on that information. So an agent that's doing that will take in its sensory information from the world around it, make a decision about what to do, return the action that optimizes something based on the underlying representation of the world that, if it's a logical agent, is a knowledge base. So that becomes the data structure of what it knows about the world around. So agent tells the knowledge base what it perceives, then asks the knowledge base what it should do. Agent is dumb agent. Agent requires knowledge base to do anything. It's like the human, the actions, and the brain. You take the brain out of the human can't do anything anymore. So much more detail about this coming, but that's the general layout of a knowledge base agent. Questions on any of this basic setup? All right. How do we set up a knowledge base agent? We have two options, and this may be familiar if any of you have studied either programming language theory or heard of different paradigms of different languages. If you've heard of the declarative versus procedural arguments, anyone for whom that's familiar? We really need a programming languages course here. So this really just becomes, how do you gather knowledge? How do you set up knowledge? If you're using a declarative process, then the programmatic overlord is telling everything. Tell sentences to an initially empty knowledge base, and eventually you've told it enough to be able to do something intelligent and derive something intelligent. So it's really setting up the world by painting it from the ground up or creating it from the ground up. There's nothing about the world. The agent isn't interacting with that initial state. The entirety of the initial knowledge is told to it. Procedural says that we are going to now give the output to the system. We want you to be able to do this and this and this and some other thing. Here is some information, but figure out how to map the information to these particular outcomes. So as we write this, we are going to say, this is the desired behavior. This is the outcome we are looking for. They kind of are at odds with each other, as you can imagine, but they can work in tandem quite well. So if you're going to implement an agent, it's worth thinking about what systems should I construct declaratively, which systems should I construct procedurally, and it turns out that this we see in programming languages as well. So I don't know where I want to go with that, but useful. It is worth noting as well that you can take a declarative system and you can compile it down into a more efficient procedural system. So you feed it a bunch of information, you say, here's what I want it to do, and it can figure out the links between the knowledge that it has, and it can create a system to create those outputs from that. So linking the declarative to the procedural is nice. And when you go to actually run this, if it's procedural in nature rather than declarative, you will have a smaller knowledge base, or you will have prescribed functions or methods as ways of doing intelligent things with that data to describe the associated behavior. The one thing that is yet outside of the scope of this a bit is machine learning. So this is all just interacting with the system itself. The system is not actively learning at this point. It's just coming up with new facts, which isn't really learning. It's just taking what you have and kind of thinking about it. But we'll go over machine learning in a lot more detail and talk about how machines can actually take information and really learn from it in a bit. So I'm curious, I know Calvin is in the machine learning course right now. Who has taken or is taking some machine learning course here or elsewhere? 3 of us. 2 of us if we take out the TA for the course, which is probably why I selected the TA for this course. The way that I did. Yay, Stephen. So we'll cover machine learning later, and that is really the modern power of this idea. So we're going to learn about this in the same way that we have other ideas, by applying it to kind of a test world or a test environment, where we can start to phrase, as we are learning, the application to that. So for constraint solving, it was this weird Australia. Who would ever want to live there, especially after what we just learned? But in this case, it's going to be the Wumpus world, which is much more fun than Australia. Not only does it not exist exactly like Australia, but now there are weird things and places in this Wumpus world. Okay, never mind. It's literally Australia. So it's a world that is an n by n grid. So a grid world, there are rows and columns associated with that world. And the agent begins at what we're going to call the entrance/exit. So you can only leave the world from the lower left corner, which we are going to call row 1, column 1. Everything's 1 indexed. And it begins facing right. So lower left corner facing right, not up. That is the initial state of the Wumpus world. Somewhere in this, so this is a dark, dank cave. This agent cannot see anything about where it is. Somewhere in this world, not at the starting location, is an unmoving, absolutely disgusting abomination of a creature called the Wumpus. It is truly disgusting. It emits a stench to every adjacent cell to its location. So if you are adjacent to the Wumpus, you can tell that you don't want to be there. It is a very smelly place being next to the Wumpus. If you move into the Wumpus from an adjacent cell, the agent perishes. Terrible. The Wumpus is just sitting there like the Sarlacc from Star Wars, just waiting for someone to fall into it to eat it, but it does not move. There are also some pits. We don't know exactly how many of them there are, but if you're adjacent to a pit, you can hear/feel a breeze. Something that says, wow, there's wind moving up, down, and it creates kind of some wind in the adjacent cells to that. Now, since we can't see, we don't necessarily know which of the adjacent cells has the wumpus and or a pit, but we can make some logical deductions about that based on the history of our actions. Of course, why would we even be down here if there wasn't a reason to be down here? There is one cell that contains gold, and it emits a glitter that is only visible from directly on top of it. So unless you are in the cell with the gold, you do not know where the gold is. But once you are in the cell of the gold, you know that you are in the cell of the gold. So the purpose of all of this is to search around, not die, find the gold, get out. We'll talk about the scoring here in a second. But what can the agent do in this world? There are a few things that it can do. There's the forward action. Depending on the agent's orientation, it moves it forward. So since you're beginning facing right, if you move forward from there, you would end up in the cell adjacent to it to the right. If you run into a wall, luckily, you don't move through the wall. That would be a little scary, but you will feel a bump percept. You do not bash your head enough to get a permanent concussion or anything of the sort. You just feel a bump and you know that you did not successfully move in the direction that you attempted to. The agent can turn left and or right. I guess not and, left or right, left X or right. It can grab. If it is in the cell that has the gold, you will acquire the gold if you take the grab action. Otherwise, I don't know, you can't grab the wumpus. You're already dead. There's nothing else to grab. Can't really grab a pit, that doesn't make sense. The agent has a bow with a single arrow. I don't know why you would lug down an entire bow but only have a single arrow, but I don't know, maybe our agent needs a little bit of training. Has a single arrow. So the shoot action fires that arrow in the direction that the agent is facing all the way until it hits something. It cannot hit a pit, so it either hits a wumpus or it hits a wall. The goal of the arrow is to kill the wumpus. Because of course, this big, scary, stinky creature falls to a single arrow anywhere in it. It's just how the wumpus works. It's kind of, it's very scary. It has a ton of offense and no defense. Its offense is like 10,000, its defense is like 1. So if it hits the wumpus's cell, we can hear it scream. And that scream can be heard from anywhere. You do not have to be adjacent to the wumpus to hear it scream. It screams loud enough before it dies to be heard throughout the cave. And yes, the agent only has 1 arrow, so use it wisely. Finally, the final action is climb, and you use that back at the entrance/exit to escape the system. You can do that with or without the gold. Questions on the grid or the actions? Yeah.
Can I do the action twice in a row, like turn, can I do that twice too?
Yeah.
Just basically.
Yeah, so the score of this game is going to be based on the number of actions that elapse before something of interest happens, like the agent dies, you escape with the gold. You fall into a pit, which is the same thing as dying, wumpus or pit, but yes, you're going to take action over and over and over and over and over with the goal of maximizing the associated score from a run of this. So how is it scored? Here's an example of a version of the wumpus world. You would ideally be able to discover the location of the gold, grab it, and get out. If you leave the cave with the gold, 1,000 points are added to your score. If you die to the wumpus or to a pit, 1,000 points are deducted from your score. When you fire the arrow, because there's no hope to ever get that arrow back, there is a cost to replacing that arrow, and that is 10. So firing the arrow actually costs you a bit. Every other action you take is going to cost you 1. The idea is we want to prioritize being efficient if we possibly can, but also being safe and trading off safety for the amount of time that it takes you to discover information about the world around you. And the game just ends whenever the agent dies or climbs out of the cave, with or without the gold. So now you see that if you explore around and then leave, climb at the end, you'll have some reasonably small negative score. Better than dying. If you're able to find the gold, it will more than make up for the time that it takes to explore around to find the gold. So it's always worth trying to find the gold rather than, all right, unless of course you don't have enough information to make an informed decision about what's safe and what's not. So you have to trade off how risky is it for me to explore a particular space with how likely am I, if I explore that, to find the gold.
Why would you want to defeat the Lumpus?
If it's in the middle of a path that's preventing you from getting past it, maybe there's a pit right next to the Wumpus and a pit next to that, and it's siphoning off the ability to explore the rest of that area. Or it might be on top of the gold, and there's no way to know without killing it and checking its square. The only way to check that square and not die is to have killed it. We're going to have a 5 tuple for our sensors. Whenever we take an action, we're going to receive the following percepts: stench, breeze, glitter, bump, scream. Each of these are Boolean. So you're going to get something like false, true, false, false, false. And that's going to tell you that in the cell that you are currently in, I feel a breeze. There is no stench. I'm not at the location of the gold. I did not just run into a wall, and I did not just kill the Wumpus. If there is, for some reason, no percept, then we will get none. We can consider that to also be false. That's fine too. So what are we going to do with this world? So it's a test bed for logic. We can apply propositional logic to this world and try to build an intelligent agent off of just propositional logic. We can incorporate predicate logic and try to build a useful agent based off of predicate logic. As we start talking about probability theory, we can start making intelligent decisions about when is it worth exploring or not exploring this particular space based on the associated payouts and likelihood of death, if we have a way to calculate that. If we need to decide risking death versus continuing exploring, that is an interesting decision. And it will depend on lots of information. How much of that can we reasonably recognize with just logic without probabilistic analysis? How much extra information do we gain from incorporating probabilistic analysis? To give you a sense, in 4x4 worlds, 21% of them are unfair because the gold is either in a pit, which is possible. You can overlay a pit on top of the gold. Or the gold is surrounded by pits and the agent can't reach it in the first place. So there's no guarantee that you can get the gold in any particular run of this game. But it would be nice if we could figure that out as quickly as possible so that we can escape minimizing the negative effect of our score. So let's talk about how would this work just using propositional logic. Maybe I should take a quick second and say, from all of the studying that we've done on catching up on propositional and predicate logic, what was the difference between propositional logic and predicate logic? Yeah.
Propositional logic is, this implies that, so it's a one-to-one. Prepositional logic is one-to-many relationship, so that X is bigger than 5. X could be all the numbers that are bigger than 5.
Yeah, okay. Yeah, propositional logic uses logical and or not implication and bidirectional implication to be able to do everything that it needs to be able to do, really. And so it's going to build rules of the system just around that. But there are no quantifications. There's no way to say every, there's no way to say some, or any kind of logical word like this. So if we need to be able to do that, we need to iterate over every possibility, and that can be a bit of a challenge and depends on the size of the world. There's no easy way to scale propositional logic on the size of the world. Predicate logic, on the other hand, will allow us to use for all or there exists, to be able to say every or some, and use that as well as functions or methods that have a particular meaning that allow us to be able to kind of summarize a lot of what we would have to do in bins of propositional logic. So we'll go over kind of how the world would be represented in propositional logic, and then we will probably not touch it much as we talk about how to extend it into predicate logic and just not really look back on the propositional logic for this, because most logical agents are significantly easier utilizing predicate logic. So purpose, we want to utilize the percept history. So as we explore the world, we'll be gathering information about the world. If we apply important initial knowledge to the knowledge base, then the percepts that we gather from exploring the space will tell us where should we explore next. Should we go escape? It should be able to return us some action like that knowledge base agent on the first slide that informs us what we should do from here, given this world. So if we're only using propositional logic, we do need this complete logical model of actions and consequences, cause and effect, all of the rules of the world embedded into this. And that is going to be a bit of a pain to set up. Well, let's talk about what that would look like, because it will be useful for when we talk about the associated predicate world. It would be great if we didn't have to parse the entire history every time we make a decision on an action that we're going to take. That would be super annoying and really inefficient. So instead, we're going to query the knowledge base and have the knowledge base intelligently return to us something useful. What do we need to be able to do? They're answering questions like, where am I? How do we keep track of location and how location is updated when certain actions are taken? Which cells are safe? We need the ability to know when I have explored somewhere, I didn't die when I was there, so I can go back to it. If I feel a breeze or a stench, this tells me something about one of the surrounding cells, one or more of the surrounding cells, to this area. We also need to know, where haven't we been? Do I know where the Wumpus is? So questions like this are kinds of general knowledge that we need to have propositional logic for. There are many more questions that you could answer, but just the knowledge of how does the world work? How does the agents interacting with the knowledge work? So how would we set up a knowledge base? Start with rule-based knowledge. You can start with something like, well, we know that the starting cell does not have a pit, and the starting cell does not have a Wumpus. So we're going to say, not pit in 1-1, and not Wumpus in 1-1. These are statements that we can make about the world that we know for sure. Since the agent starts there, it would be especially unfair if we killed the agent on the first turn. So we're not going to do that. We need to figure out, okay, how do breezes, stenches, pits, and the Wumpus, how do they affect each cell? So you would do something like, if there is a breeze in 1-1, it implies there is either a pit in 1-2 or a pit in 2-1. This is a logical OR, not a logical XOR. And that's bidirectionally implied. So if there is a pit in 1-2 or a pit in 2-1, it implies there is a breeze in 1-1. Using the words implies, it's just if then. If there's a breeze in 1-1, then there is a pit in 1-2 or there is a pit in 2-1. If there is a pit in 1-2 or a pit in 2-1, then there is a breeze in 1-1. So implication is just an if then. Similarly, for stenches, if there's a stench in 1, it implies the wumpus is in 1, or the wumpus is in 2, Bidirectionally implied, if there's a wumpus in 1, or a wumpus in 2, then there must be a stench in 1. We would want to be able to state something like, there is only one wumpus in this world. There aren't 10 wumpuses. Once we've discovered where the wumpus is, we want to be able to state that there is no wumpus anywhere else. We want to be able to derive that information from the knowledge base. So, this is a bit challenging. How would we state that there is exactly one wumpus? Any thoughts on how you could design this with a series of propositional logic statements?
You would explore spaces until you could map where stenches were coming from.
This is even before the agent sets foot in the world.
Okay.
If we're setting up the knowledge base, we want the agent to know that somewhere in this world, there is exactly one wumpus. How can we encode that before the agent even starts forward, left, right? Because as soon as it's moving, it needs to have knowledge of the world around it to be able to infer what it should do. One of those important pieces of information is there is one wumpus and there is not more than one wumpus.
Could you say if there's one wumpus in any spot, that implies no wumpus in every adjacent spot?
Yeah, so that's certainly a good start. So we need to state a couple of things. There is at least one wumpus and there is at most one wumpus. I think that helps in answering that question. If the wumpus is here, then it's not a bunch of other places. That can be broken down into these two components. And answering these two components says exactly that. So the first is we can say, using an inclusive or, this says that there is at least one wumpus. Do we see why that is?
Yeah, because it has to be some.
Yeah, so these are logical ors, inclusive ors. So this is saying there's no way to not have a wumpus. There's a wumpus in at least one of these cells. So this is at least one wumpus. How do we say at most one wumpus? We have to say something like, using every possible pair of cells, at least one of those doesn't have a wumpus in it. If this seems kind of silly, welcome to propositional logic. As the world scales from a 4x4 world to a 10x10 world or a 100x100 world, this gets stupider and stupider. How do we represent things like where the agent is going to move? We need, for every single possible cell and orientation, we need to be able to update the agent's location when it does things like move forward or turn left or turn right. So you can see that there's just a ton of information that we have to dump into this knowledge base initially. And there are a ton of statements, all of which are true in some regard.
What was the point of the screen?
Scream tells you that the wumpus has been hit by an arrow. So now you can, as the agent, move into the wumpus's cell without dying.
It only screams.
Yeah, that is literally the only time that the scream percept is heard. You hear it at most once, and only after you fire the arrow. On the turn right immediately after you fire the arrow, yeah.
Does the snow go away once the wolf is dead?
No, it does not. There are still stench percepts, but you need some way to determine now that that does not matter. Because the wumpus has been killed.
You said.
I would say the stench gets worse as the wumpus, who is smelly when it is living, starts decomposing. Although I guess if decomposing is worse than the wumpus's breath in the first place, says something about how disgusting the wumpus is.
How does the wumpus kill you?
It eats you.
It's like let's go with it, something like a raincore. It starts.
How do we say the wumpus will kill you like a rancor with propositional logic?
I want to go.
We have to go through every other organism and say it won't kill you this way.
Oh,
Yeah.
Every other possible organ. You will find these kinds of constraints on propositional logic in general. We have to define the boundaries of the system because the system cannot define the boundaries of the system for itself or propagate past what you define. which is kind of a problem.
So we're building up this knowledge base, right?
Yeah.
So is this assuming that we've communicated everything clearly as a fact without any,
These are the facts.
okay,
You, the programmatic overlord, are listening to me tell you about how the Wumpus world works. And you're building this knowledge base, saying, when in English, I say there is exactly one Wumpus. You add all of the following statements to the knowledge base. And that is the propositional logic equivalent to my being able to say something that you can logically infer very quickly.
so,
I guess we'll follow up.
so based off of earlier stated motivation, how do we inject that, that sense of we built this fact, now we can ingrain some whys into it?
Yeah, well, if I say, if any of these are wrong, then you're gonna find that your agent thinks that it is safe when it is actually not safe. Or there's gonna be some assumption that it makes about the world, that it can infer perfectly logically from the information that it was given. But if the information it was given was wrong, then any decision that it decides may have unintended consequences. It may act suboptimally. Imagine the very first thing your parent tells you when you are born and you have the ability to perfectly understand everything that they say is, this poison in the cupboard, it's candy. If you believe them, you're in for a treat. You think that you're in for a treat, and what actually happens is very different from what you expected because you were fed false information. So the outcome of this is not the outcome that you would have assumed it was going to be from the information that you got.
Dealing with the logic there, how does it not just say that it's between 1 and 16 Wumpuses? Because it doesn't say there has to be at least one cell has a Wumpus, and not
Yes.
every single cell has a Wumpus, so that implies that every single cell except one could have a Wumpus at the same time.
Not and have all of these statements be true at the same time.
So only one of those statements can be true at the same.
All of these statements have to be true.
All of them have to be true.
Yes, and if every single cell has a Wumpus except for one, let's say that it's in 4,4, then this statement is not true. There would be a Wumpus in both of these locations. The only way for this statement to be true is if there is the lack of a Wumpus in one of those two cells.
Okay, so that's just saying there can't be a Wumpus in this cell or this cell for every combination.
Right. Which paired with this says that there's exactly one Wumpus.
I see.
There's at least one Wumpus and at most one Wumpus. At the same time, if both of those are true, then there must be exactly one Wumpus.
I see.
So, great. We need to store the entire state of the world, laying out how every potential change affects the entire world for every cell, for every possible action. And you start to see how this scales exponentially with the size of the world, with the number of actions that you can take. It's a bit of a problem. So what we can try to do is now say, all right, we're going to introduce a new variable, time. And we're going to try to state how a particular action at a particular time will affect the next segment of time. We're going to discretize this world to a time step action, time step action, time step action. And can we reduce the size of what we need to do to this knowledge base if we change the world in that regard? So time ends up being a very important component of propositional models in general. We can define the concept of an effect axiom as saying, all right, what happens if we take an action? What happens in the next time step? So you could do something like L here stands for location. If we are in location 1, 1 at time 0, that's what that first statement is saying, and we are facing east at time 0, and we are choosing the action to move forward at time 0, that implies that the location at time 1 will be 2, 1, and the location at time 1 is not 1, 1 anymore. You can imagine, of course, that since we've discretized this, is there any variable for the associated time? no, we can't store that, that's variabilized, propositional logic doesn't allow for that. So now, depending on how long this is going to last, we would have to duplicate this for every possible time step. So removes one axis, but kind of adds another one in that we need sentences for every time step, for each square, for each orientation, for each action. But we don't need to combine them all into a single state. Cool. As an example, let's say we assert to the knowledge base, the agent is in 1-1, moves forward. With everything that we've done so far, we can now actually deduce where the agent is. We can determine its location. We would state that this is happening based on that. So we can imply that this is the actual outcome based on everything that we know about the setup of the world. Cool. If you ask the knowledge base, what is the location of the agent at this time, it would be able to return to you, you are in 1-2, based on the setup of the world, which is kind of cool that we're even able to do that in the first place.
Is this row, comma, column?
Yes, yeah,
It's facing
row
right.
column. Is it? It's facing right and then it's moving, so it must be, it's column oriented. Column 2, row 1. It has to be as confusing as possible. Again, I'm trying to use the exact same notation as the book. I don't love it. I like zero index. I like row before column. I like starting in the top right, or sorry, top left rather than bottom left.
Row before column, isn't, if it's facing right and moves over one column.
Right, so the column will be what changes since it comes first.
Oh, you mean like column before row?
Yeah,
Okay. I think you said it.
yeah, I did say it, but
Got it.
yeah, it's the X first, X then Y.
Yeah.
And even if we do all of this, there are still some arrow issues that we might need to figure out based on what do we know after things like we fire the arrow. So we can use what we're going to call frame axioms to do that. And this helps to solve things like memory retention issues, where in one time step, you know that you killed the wumpus, and in the next time step, you have no idea if you killed the wumpus. So you could do something like, when I move forward, if I had the arrow at time t, then I would have the arrow at time t+1. And of course, you would now need to duplicate that for every possible time step that you could have, but assuming we could variabilize it, then this would help you if you had this programmed in, that you would be able to retain the memory of, if I have the arrow, then I will still have the arrow until I do something called shoot the arrow. If I move forward and the wumpus is alive, the wumpus will still be alive in the next time step, because the only way the wumpus is not alive is if it is shot. I don't know what the difference is between alive and alivey, but I'm sure we'll figure it out. So anytime that you have an effect that the cause can't have, so if we move forward, the effect that the wumpus is now dead is impossible. So we can encode that as something in the knowledge base, and now the knowledge base has memory that is based on just this logic, which is kind of interesting. If we think this way, we can start to reduce the size of what we put in the knowledge base in the first place, and start thinking about the world in terms of cause and effect instead of state. And some of what state is represented as can now be cause and effect. If it's smaller in cause and effect, saves time. What we call fluents, just parts of the world that are capable of changing over time. So we can call, this is called successor state axioms, determining what can change in the world. If things can change, then maybe it's worth thinking about it in terms of frame axioms. And that frequently is better than trying to bake it into the state, because now we would have to say, have different propositional logic statements for something, and Wumpus is alive when we move forward, we're still here, and Wumpus is dead when we move forward here. If we can factor that variable out completely, that dimension out completely, if we think of the Wumpus being alive as its own frame axiom. So you can think of it as removing a dimension from the dimensionality of this problem, which is an exponential time speed up, which is great. So here's what that would look like. If we moved forward at time t plus 1, that implies that the action that caused us to get to time t plus 1 from where we were at time t means that whatever action can't happen at time f when we would at time t when we move forward, that means that that can't have happened if we chose forward at time t. So this is kind of a general way to create a fluid. It just maps directly onto that logic. So here's an example of applying that. If we have the arrow at time t plus 1, then we had to also have had the arrow at time t, and we did not shoot. Because if we had shot, then we would no longer have the arrow. So it's a way of determining from the state of the world something that couldn't have happened. And because of that, we don't have to worry about whether we have the arrow. Having the arrow is now strictly a measure of, do we still have the arrow? We can determine based on the action shoot that we did, now we can tell that we no longer have the arrow. Location is also kind of annoying. So location 1, 1 at time t plus 1 implies location at t. If we were also here, that implies that we did not move forward or we didn't get the bump. So if we're at the same location that we were, one of two things must have occurred. Either we didn't move forward or we tried to move forward and weren't successful. And you can do that for all sorts of actions, and we can start to factor those out in some capacities. So the goal is just to remove as much complexity as you can from the knowledge base. Questions on anything we've said so far? Just logic dump. Very interesting.
Yeah.
No.
I mean, it's interesting. I just said very much so.
Yeah.
As in, yes, you've logic dumped me.
Yeah.
If I have to understand this in any way other than like, this way's kind of overcomplicated and stupid, this other way's better, good. But it's making like sense. So
That's good.
It's like crazy that bump t plus 1 is used in logic. So
Yeah, right?
referencing the future.
Yeah. Yeah. So determining that a cell is safe, that's something that you could also put in terms of one of these frame axioms. So cell XY is safe at time t if there is no pit at XY and there's either, so it's the negation of the wumpus that is at XY and the wumpus is alive. So either the wumpus is not there or the wumpus was there and is dead, is the other way to state that. So that defines what it means for a cell to be safe. That's cool. We can now factor it out from doing that a bunch of times in combination with every other variable. What's great is if we can apply all of this, but as soon as there is uncertainty in your domain at all, it becomes very funny very quickly. Like, we're assuming that when we make the forward action, we're not doing something outside of the scope of the rules that have been defined so far. The agent trips and falls. What if the agent is carried away by giant bats? Just something that we didn't consider in the rules of the system. We don't have rules for what happens when something unexpected happens. If the agent has a heart attack, there's no action that's defining how we should handle this. So how does propositional logic handle something that is not anticipating or not expecting? And the answer is, it doesn't. You have to manually try to find what could go wrong and specify what to do if something goes wrong. And the issue with this is that if you try to do this for everything that could go wrong, usually there are so many things that could go wrong that it's not worth trying to figure all of that out. So you need to figure out where that line is, usually using some kind of probabilistic analysis. If it's kind of likely that this thing that could go wrong, let's design a solution to that. If it is less likely than that, it is okay for our system to just spin and not know what to do, because there's no way to bake that into the system itself. So we'll come back to probability theory and try to revisit this a little bit in terms of how can we determine what to do and what to not do. That's probably a pretty good place to stop. So I think we'll come back to this on Tuesday and talk about it in a bit more detail, and then eventually go apply this to writing a Wumpus World solver.
This can is.
Luckily, we're not going to be doing it in terms of just propositional logic.
All statement is true for all, and then you gotta apply it.